In the previous session, you have learned the implementation of the state machine in the AXI OCP converter module. Now we'll go through the other part of the AXI OCP module. So in the port list of this module, you have clock and reset. Then you have five set of interfaces coming. So the write address interface 1 and write address interface 2, and write data, write response interface and read address interface 1 and 2 will be coming to this module, which are directly tried from the top module. Note the write address, write data and read address interfaces are of slave mode port, and the write response interface is of master mode port, and because we are driving these interfaces from the internal submodules. So you had already seen that once you passed a write address, write data and write response interface to a module called AXI Right Front End, it will take care of synchronizing the address and data coming through the address and data channels based on the ID or the tag, and it will be saved into a FIFO, and again a valid indication will be given to the output, saying that complete write packet is available with a valid signal. And also it will take care of driving the response interfaces, which we had already seen in the description of AXI Right Front End. Since you had defined this module, your job is reduced to just instantiating this module in the upper module, which will take care of a set of AXI channels coming into the DUT interface. Thus, we will instantiate AXI Right Front End in the AXI to OCP converter. So these are the internal signal defined, and these are the state machines which we had already covered, and after that we will instantiate the submodules here. So AXI Right Front End is instantiated with name AXI Right Front End 1 and 2. To front end 1 we are passing the address interface 1, the data interface 1, and the write response interface 1, and to the instance 2 we are passing the AXI write address interface 2, AXI write data interface 2, and AXI write response interface 2. Thus these modules will take care of saving the whole address packet internally and forming a complete write packet. And in the same way, by instantiating the AXI Read Front End module twice with the name AXI Read Front End 1 and 2, and passing the interfaces, that is the AXI Read address interface 1 and AXI Read address interface 2 appropriately, these two modules will take care of storing the incoming AXI read packets and giving a complete read packet information to these outputs. So now your job is to connect the output and input of this module correctly so that the functionality is achieved. We will again go back to the right front end module. So here you had the interfaces coming in, and you will have a hold in coming in, and the output will be a complete write packet and its valid signal indication. And you can see that this hold in is to hold a hold in will be used in the read part, that is AXI FIFO read enable part. So whenever there is a hold in coming, we will not read out from the FIFO. Thus you need to drive the input hold in correctly so that this is tied to 1 if the current client is not served at this point. So we will see it here in the AXI OCP converter. You can see that the hold in is driven with a signal name hold right front end 1 and right front end 2, and hold read front end 1 and read front end 2. Now we will see how the hold right front end 1 is derived. The hold right front end 1 is equal to whenever the arbiter current state is not in the C1 write. So whenever the arbiter is deciding an arbitration to any other clients, at that point we will raise a hold to the right front end 1. And also in case of write, you need to pop from the FIFO only once to get the complete packet. Once you have popped out the first entry, you need to wait till all the data has been sent to the OCP client. Thus whenever the arbiter current state is not in C1 read, and if it is not the beginning of the AXI OCP write start, you will raise a hold into this first module. And in the same way, the hold for right front end 2 is assigned, and also the hold for read front end 1 and read front end 2 are assigned, like arbiter current state is not equal to C1 read or C2 read. And C1 read it will complete in 1 clock, because there is only one address need to be transmitted. Thus, you don't need to take care of the condition similar to the start of a write. And also you have seen that in all this whole equation there is another OR part. Whenever the OCP client is not ready to accept the next data, that is the OCP command hold is equal to OCP interface.s command accept. So whenever the OCP client is indicating that it is not ready to accept that data, we are raising hold in all these equations so that the next entry will not be popped out from this internal FIFOs. Next we will go through the read part transmission. So you can see that from the read front end 1 and 2, you are getting a packet valid information in the VLD underscore RDFE1 signal, and the complete read packet will be available in packet underscore read front end 1. So you need to transmit this packet in the OCP interface. So this is the driving part of the OCP. So again, I am deriving another signal called read valid. Whenever we are sending C1 read, or we are serving C1 read or C2 read. So whenever the arbiter current state is equal to C1 read or C2 read, we are saying that the read valid, and the current read packet will be equal to, if it is the arbiter current state is equal to C1 read, then the current read packet will be equal to packet underscore read FE1, which is coming from the read front end 1. And if the current state of the arbiter is C2 read, then the read packet will be equal to packet underscore read FE2, and this read packet will be sent to the OCP interface whenever the current state is read, or whenever the read is valid. So you can see that in an always COM, OCP interface m command is equal to, if it is read valid, the command is equal to read, and if it is write valid, the command is equal to write, otherwise it's idle. And the address is equal to, if it is read valid, the address will be equal to read packet dot address, which is nothing but, if it is C1 read, it is equal to read packet 1, and if it is C2 read, it is this read packet will be equal to the packet coming from the read front end 2. And if the read is not valid, and if the write is valid, the m address will be equal to write packet dot address, where write packet is equal to the packet coming from the right front end 1 if the current state of the arbiter is C1 write, otherwise and the current state of the arbiter is C2 write, it will be equal to packet underscore the packet coming from the right front end 2. And in the same way, the bus length is equal to, if it is read valid, the bus length is equal to read packet dot length, otherwise if it is write valid, it is the AXI write packet length, which this we will see next. And again, the tag is equal to, if it is read valid, read packet dot ID, if it is write valid, it is write packet dot ID, otherwise it's X. And the data valid will be equal to 1 only if it is a write. So if it is read, the data valid will be equal to 0, and the m data is again valid only for a write. So the m data, if it is a read valid, then it is X, and if it is a write valid, the current data or m data will be equal to AXI to OCP write data dword, which we will see in short. And again, m data last is equal to 0 if it is a read valid, and if it is write valid, the m data last will be equal to AXI to OCP write end signal, again which you are going to see. So the reads were quite simple. Based on the current state of the arbiter, you just need to take one of the read packet coming in and send it to the output. And again, for write packets, you can send the address immediately. To complete the data transfer, it will take multiple clocks. So in case of write valid, you have seen that the m data will be equal to AXI to OCP write data dword. So this variable is an output of a 16 input multiplexer. So this is an output. This output is selected from any of the 16 inputs which are D0 to D15 based on the current value of the AXI write count. Now you will see what all are the inputs. So you can see that D0 is equal to write packet dot D0, where write packet is equal to the current write packet selected from the right front end 1 and 2. Once you release a hold to any of the right front end ones, the FIFO will be popped out and the current write packet will be available. So once you read out from the FIFO, from the next moment onwards, the FIFO will be pointing to the next entry in its internal storage. Thus the packet underscore WRFE1 and WRFE2 will be pointing to the next entry in their FIFOs. Therefore, we are using flip-flops to save all the data from D1 to D15 of the current packet. D0 is equal to current write packet dot D0, but all the values from D1 to D15 has to be saved into a flip-flops uh, to get the correct value for the data. Thus we are using 15 flip-flops, and I have used, instead of listing out 15 them separately, I have used a single macro instantiating with the within a bracket. So we will be getting all the write packet dot D15, D14, D13 values into this variables or flopped variables D15, D14 and D13, and you can see that the input to this multiplexer will be the flopped version of the D0, D1 to D15 and the current value of the D0. So these are the input to this multiplexer. The output is the current data pack that is going into the OCP, and the select line of this multiplexer is AXI right count. So this write count will be equal to a flopped value of the write count previous, which will be incremented in every clock whenever there is a valid data transmission. So you can see that AXI write count previous is equal to, if it is an end of write, then the next next value will be equal to 0. Otherwise, if it is a valid write going on, that is the arbiter current state is in either C1 read or C2 read and there is no OCP hold, in that case the next value will be is equal to AXI write count plus 1. Otherwise the next value of the AXI write count is equal to the current value. So based on this AXI write count value, one of these data will be selected and it will be sent to the OCP interface. Now again you can see that these signals AXI OCP data write start and write end are derived. So the write start is to detect the starting point of write packet sending to the OCP. So that is when the arbiter current state is equal to C1 write and 0 is equal to AXI write count, or arbiter current state is equal to C2 read, C2 write, and C0 is equal to AXI write count. So if in that case it's a starting point of the write, and that is the point where we release the hold to the right front end. In the same way, AXI OCP data write end is equal to when the states are in C1 write or in C2 write, and the AXI write count is equal to total length minus 1. So that is the point where it transmitted the last data to the OCP interface. So these two signals, AXI write start and write end, are again derived to make the coding a little more simplified. This completes the description of the AXI to OCP converter module. So as you had seen, you have a state machine in the initial part, then the logic to take out one of the packet and send it to the OCP client. I have added a snapshot of this code at the end of this session.